Hello and good evening, everyone. I'm Hirah Malik. I'm a PhD student at the University Paris-Saclay, and I work on the general topic of information-centric networking and network coding. Today, I will be presenting my work that combines these two topics. This work has been carried out at INRIA and LUZES under the supervision of Professor Michel Kiefer, Cedric Adji, and Claudio Wiedemann. And this work has been partly funded by DigiCosme and INRIA. I will be starting with a short introduction of information-centric networking. The traditional internet paradigm is based on point-to-point communication, where a user communicates with a specific location on a secure channel. It's host-centric or location-centric and addresses endpoints. So each endpoint in an IP network is assigned a specific IP address. For example, this URL here translates into this destination IP address of the Dailymotion server. Information-centric networking was initially introduced around 2006 by Wen Jacobson as a new way to look at the internet. The core of information-centric networking is routing content by names. ICN names content instead of location. Unlike IP, in information-centric networking, consumer sends interest packets carrying the name of the content that they require to the network, but the consumer doesn't know to whom they send the interest. Anyone that hears the request and has a valid copy of the data can respond by sending the content in a data packet. So ICN has two main communication messages, an interest packet and a data packet, one that carries the requests and the second one that carries the content. Named data networking, or NDN, is one of the implementations of ICN, and we use NDN for our project implementations. So let me give you an overview of the NDN semantics, starting with an NDN node or an NDN router. An NDN node has three major data structures that help it work. First of which is a forwarding information base, or a FIB. The FIB stores the routing information, and it's used to forward interest packets toward the potential source of the matching content. Pending interest table or a PIT keeps the record of pending interests that are forwarded by the node, and the data that's stored in a PIT helps the router to route the content back to the requesting consumer. A content store is the cache memory, and each NDN router is connected to the neighboring routers through several interfaces. Moving on to the semantics, as stated earlier, the content is requested to names that are sent in interest packets. So a consumer that requires any content forwards an interest packet. This interest packet is forwarded in the network by the neighboring routers using the information that is stored in their FIB. And it's forwarded unless it reaches a router, a node that has a stored valid copy of that content, which in this case is this producer here. The producer or the router then sends the content back in a data packet. This data packet is routed back to the consumer following the path of the interest to reach back to the consumer that has requested it. One important thing to note here is that ICN allows caching throughout the network. This is one of the important properties of ICN or NDN. So the routers that routed the data in the past can choose to cache it, as here in this example they cached it. So the advantage of this is when another consumer requests a same content with the same name, it can retrieve it from a router nearby instead of having to go all the way back to the producer. So one of the key benefit of requesting the content by name is that it removes the need to establish a session between the client and a specific server. So the content now can be retrieved from multiple sources. However, in a dynamic network with multiple sources that are uncoordinated, NDN cannot benefit fully from the multicast property. The reason being that the paths are well defined in IP. In IP, we have well-defined routing paths, while in ICN, we don't necessarily have well-defined paths. In most cases, ICN does not have well-defined fib. So, example here, a consumer that has to retrieve content with two source segments, A and B, sends the interest on the available paths, but ends up getting twice the same content, which is just redundant content. A good solution to benefit from the multipath property is network coding. So, just for a brief introduction of network coding is a paradigm that allows combining packets in the network. Packets can be combined in many ways. They can be XORed, can be added, or the nodes can perform linear combination. Coding and recoding is allowed throughout the network, and decoding is easy. It's usually performed by solving linear system of equations. Once a node has received enough coded packets to perform inverse operation, it can decode to recover the original segments. Now, with network coding implemented over NDN, the user forwards interest for coded content instead of just simple content. So to retrieve this content with two source segments A and B, the user sends out an interest for coded content, and coded packets are sent in response. For example, here two coded packets Q1 and Q2 are sent. Once the user now use these coded packets to perform, the user can solve linear system of equations to retrieve the original segments A and B out of these coded segments. This can only be performed once the user has received enough linearly independent coded packets to retrieve the original segments. The idea of using network coding over ICN or NDN, it dates back to 2012. It has proved to improve the performance of ICN or NDN, and several protocols have been proposed in the past, but they do not address all the issues with network coding. Currently, there is ongoing work in standardization on the precise topic of mixing of network coding and ICN in IOTF, Network Coding Research Group. So for some context of the issues on implementing network coding over NDN, one important thing to keep in mind is that now the packets, the coded packets are mixture of source packets. So one interest packet can be responded with many differently coded packets. And for, as I've said already, an n source segment content, and linearly independent coded packets are required to decode the original content. To perform the inverse operation or to retrieve the original segment, at least n linearly independent packets are required by a node. In case of NDN, the problem occurs because we have caching, as I've said already. So now a consumer, when sends out the first request for a coded segment that reaches a source, it gets back a coded segment. This coded segment may be cached anywhere in the network. For example, here, this intermediate router caches this coded segment. And now when the user requests another segment, another coded segment, it might end up getting back the same coded segment from a router that has cached this coded content. And this is a problem because this is redundant content. This is linearly dependent content. It is useless for the router. One way to solve this problem is that we can limit the routers from sending more linearly dependent content more than once. But this problem can happen anywhere in the network. The user or the client can end up getting linearly dependent content from anywhere in the network. So the main idea of the project that or the work that I'm going to present today was to implement or to have an efficient network-coded NDN that allows multiple parallel interests and ensures that for each of the multiple parallel interests that are sent in the network, we get back linearly independent coded content, no matter where the content is coming from in the network. So to achieve this aim, the main steps were first to mathematically ensure such properties, and then to design a protocol variant of network-coded NDN. So the main goals of our work are to be able to retrieve large content in a network where no topology is known, so we don't have a developed fib, and we want to be able to exploit all the available paths by sending interest on all the available paths, and we use the forwarding strategy which is multicast, so we send interest over all the paths. We propose a special construction of interest, Malik, which stands for multiple interests for linearly independent content. The idea is to send interests such that they bring back content from predefined subsets. So initially, we define subsets with all the possible combinations following some constraints. And to request content from these subsets, we send index interest. So an interest I1 brings back content from the subset A1, from I2 brings back a content from subset A2, and so on. So this is how we define our subsets. For a source segment, for a source content with three source segments, for example, P1, P2, and P3, subset A1 is defined such that the segment P1 should be present. It cannot be absent. P2 and P3 may be present. For the subset A2, P1 should not be present, P2 should be present, and P3 may be present. Now, if a consumer, a user, a node receives responses to interest I1, I2, and I3 belonging from A1, A2, and A3, and we stack them together, we can see it clearly that these three content packets coming from A1, A2, and A3 are linearly independent. This is the first goal of a network-coded NDN protocol. But this happens if we get one of each. What if you get two copies coming from one subset? For example, if a consumer has received packets coming from subset A2, for example, here a consumer has received C2 and C2 prime, both belong to the subset A2, and it use these two to construct something from the subset C3. In case the answer in case of Malik is likely yes. So, for example, here this user has received two differently coded packets, C2 and C2 prime. Both of them belong to the subset A2, but it can use Gaussian elimination to construct another content that belongs to subset subset A3 now. Since recoding is allowed anywhere in the network, so this phenomena can happen also anywhere in the network. For example, this intermediate router here receiving two packets coming from subset A1, C1 and C1 prime, and use it to construct content in the subset A2. And now when any consumer requests content belonging to subset A2, they can just send it from its local cache. We did a detailed mathematical analysis for such cases, that if a node receives L packets chosen randomly from K different subsets, what is the probability of them being linearly independent? This is the mathematical notation, but to show you the results of this above analysis, we have this scenario here where a user has two paths and it wants to receive a content that has 100 source segments, and if it sends interest for 47 initial subsets over 2 phases and receives replies randomly chosen from these subsets, the probability of receiving linearly dependent content is significantly low. Similarly, for the same scenario, it sends the user sends out 50 interest for the first 50 subsets, which is receiving a total of 100 content packets. The probability of them being linearly independent is still relatively low. Using the above described interest construction, a complete network-coded NDN call was implemented. We implemented our simulator in Python. It included a generic packet network simulator, on top of which we developed an implementation of the proposed protocol. We call it MICN. This is Malik ICN. We started with the classical NDN and implemented network coding on top of that. But in order to implement the ICN, we had to change most of the semantics of NDN. That includes, first of all, the content, because now it's divided in generations and is coded. We changed the cache memory of the routers, because now we have coded content. Consequently, the routers have to do more than just caching and forwarding. They have to do coding, decoding, and perform online decoding as well. Algorithm was implemented to satisfy the constraints for each interest, and the interest had to change because of index. And most importantly of all the data structures were updated, and interest and content processing, including a big part of which is queue management. To test our protocol, we have this topology with one source and several caching routers and 5 consumer nodes, as shown here in gray at the corners. These users request same content with 100 source segments, where there are multiple available paths. And so this graph here shows the rate at which each node receives number of linearly independent content. So x-axis has the time units, whereas the y-axis has number of linearly independent packets that each node is receiving per unit time. As we have 100 sources, so each node requires 100 linearly independent packets. You can see that the curves here are linear, but when we looked into the detail, we saw that all the clients are in fact receiving the content at their maximum possible throughput. Although we were able to achieve maximum throughput and we were able to get back linearly independent content, each interest that we were sending out in the network, but we observed that the old interests in the network were causing a lot of redundant traffic in the network. In order to optimize or reduce this redundant traffic, we introduced a variant of this protocol, which we call MICNI or MICN interest cancel. It cancels these old interests by adding an optional field in the interest that carries a bitmap of the content that has already been received at the consumer node and cancels out the old interest. As a result, we were able to reduce the total traffic in the network by quite a lot. As we can see here, the MICN cancel has very less redundant traffic compared to MICN. And then we compared it to one other protocol, netcode CCN, which combines network coding and ICN and also reaches maximum throughput at the consumer nodes. To conclude, we presented MICN, which is a new approach of implementing network coding over NDN. Everything for this protocol's performance relies on our mathematical construction of subsets, Malik, which helps us avoid the redundant content and achieve maximum throughput by receiving linearly independent content with each interest. For future work, we are working on improving the interest forwarding algorithms to reduce the number of interests in the network and consequently the data traffic in the network. Thank you, and I'll be happy to answer any questions.
Thank you, Hirah, for the for the nice presentation. Is there any question or comment?
Thanks for your presentation. I'm not so fluent in information-centric networks, so I may ask something which is not directly applicable. But can you generalize fountain codes to do the same multiple fountains with purely random coefficients? How do they compare, in your opinion, to the protocol that you have devised?
Okay, I'm not expert in fountain codes, but the only thing is that what we found out during our search for the right way to code the our content was that they cannot be. We cannot have purely random codes. This is why we be able to get every time linearly independent content in response to the interest. We cannot have purely all the coefficients cannot be chosen purely randomly.
You can compute the probability of failure of decoding or of receiving the whole message if you use random coefficients, right?
Yeah.
Okay. Thank you.
This linearly independence is an assumption, right? Or this comes from the nature of the problem itself?
So it comes from the linear independence comes from the nature of the problem. So if you are receiving network coded content, for any node, for anyone to be able to decode the actual information out of it, you need linearly independent content. At least for example, for a 3-segment content with 3 source segments, for example, here, we need at least 3 linearly independent combinations to be able to decode the actual information.
Okay, thank you.